Evaluate the indefinite integral. Here it is, the indefinite integral right there, negative 24x to the fifth dx. Now what the indefinite integral does is it does the reverse of a derivative. So with the derivative, we would see something like this and think power rule. Well, the integral has its own version of a power rule, and it looks like this. I'm going to let a be a coefficient, x is x to the n, and dx is basically just telling you, the end. When you take the integral, the indefinite specifically integral, because there is a definite integral, you'll see videos on that later on, what you do is the a is just kind of there. You multiply everything to 1 over n plus 1, and then you add 1 to the n. Guess I should do that. And you add this arbitrary c. Now, what's that c stand for? A constant. You have to put plus c on an indefinite integral because that c could represent any constant that we just don't know. So the way I apply that here is if I want to take the integral of negative 24x to the fifth, my a would be negative 24. I'm going to multiply that to 1 over, there's my n, 5 plus 1, x to the 5 plus 1. Close it, add c. Negative 24 times 1 over 6, x to the 6 plus c. And that negative 24 times positive 6 becomes negative 4, x to the terrible looking 6 plus c. That's my answer. As time goes on, you could do some mental math and realize that when you do stuff like, add 1 to 5 and bring it down, that will become automatically negative 4 as time goes on, but let's not jump the gun. Okay, that's the power rule for the indefinite integral. Evaluate the indefinite integral. Now, if we are given an indefinite integral of a polynomial that requires power rule for one of them and power rule for the other, you're just going to take the integral of each. Okay, there's basically a rule that says if I'm going to do this, then I'm just going to do this. Negative 9x squared dx plus the integral of 10x dx. Now, as time goes on, you don't need to write out all of this. You can just realize that you're doing the integral for each one on its own, but why not have some fun? If I were to use the power rule, what I do is I bring out a negative 9. I write out 1 over the exponent plus 1, x to the exponent plus 1. Right? Normally I would put a plus c here, but I'm going to save that for the very end because I have another indefinite integral that I have. So I have a 10. I have an invisible 1 for my exponent, so why don't I just put that there? So 1 over your exponent plus 1, x to your exponent plus 1. Now I'll drop that plus c. So this leaves me with negative 9 times 1 over 2 plus 1, which is a third, x to the third, plus 10 times 1 over 1 plus 1, which is a half, x to the second, plus c. Do a little bit of simplifying. Negative 9 times a third is negative 3, negative 3x cubed, plus 10 times a half is 5, 5x squared, plus c. And we can see if we wanted to do a quick derivative of this, multiply 3 times negative 3, we do get negative 9x squared. Multiply 2 times 5, we do get 10x. And take the derivative of any random constant, you do get 0. We did it right. That's my answer. That's the indefinite integral of a polynomial. Evaluate the indefinite integral of negative 5 cubed root of x squared over 3. So let's do a little bit of rewriting. Okay, let's write this out as negative 5 thirds. And let's turn this into x to the 2 thirds dx. Where did I get that 2 thirds from? A cube root becomes an exponent of a third. A square becomes an exponent of 2 still, so 2/3. Now what I'm going to do is I'm going to use the power rule on this guy. It's not going to be pretty. Not going to be pretty. Let's bring out the negative 5/3. I have 1 over. Now I'm going to add 1 plus 2/3 x to the 2/3, plus 1, plus c. Okay. Negative 5/3, still. 1 plus 2/3 is the same as 3/3 plus 2/3, so we can write this out as 1 over 5/3 x, 2/3 plus 1, again, same exact thing, 5/3, plus c. 1 divided by a fraction becomes its reciprocal. So this becomes negative 5/3 times 1 over 5/3 is 3/5. How convenient. X to the 5/3. Why is that convenient? Well, 5/3 times 3/5 cancel each other out. So we get negative x to the 5/3 plus c. And many teachers, professors might be okay with this, but if they want you to change it, you can write this out as negative cube root of x to the 5th plus c. Either one of these are acceptable, but there they are in both of its forms. Fun. Evaluate the indefinite integral. So I have 3x to the negative 1. Now let's be careful. I can rewrite this out as this. And normally I like having an exponent there. Normally I'm turning this into this, but the reason why I'm writing this out is because of a rule that says that the integral of 1 over x is ln of x with the absolute value. So if I wanted to be super picky math teacher, what I could do is I can bring out that 3, because you're allowed to do that with integration, and that leaves me with 3 times the integral of 1 over x dx, which means, according to this rule over here, I get 3 times 1 over x So that means I get 3 times ln of the absolute value of x plus c. That 3 times ln of x just gives me 3 ln of x. And if you're like, should I distribute the 3 to the c? No, because we don't even know what c is. Just leave it like that. Technically, it's not wrong if you wrote out 3c, because again, it's just some arbitrary constant. But we don't have to. And so that's our answer. We just did the indefinite integral of x to the negative 1, also written as 1 over x. So the integral of x to the negative 1 is ln of x. Just be careful, because it's tempting to do the power rule. No power rule here. Evaluate the indefinite integral of negative 5 sine x. Now you might remember from back in the day that the derivative of cosine x is negative sine x. So it would make sense to us to say that the derivative of sine x, positive sine x, is going to give me negative cos x. Let's put the dx there to make it complete. Let's put the plus c there to make it complete. Now, why is all this important? Well, if I wanted to write this out as a picky math teacher, I can rip out that negative 5 and say the integral of sine x dx. That's a d. I need my x first. So there you have it. So I can now use this rule, -5 times the integral of sine x is negative cos x. There you go. Plus c lives right there. -5 times negative cos is +5 cos x plus c. So that, ladies and gentlemen, is the integral of a sine function. Bada bing. Evaluate the indefinite integral of -3 cosecant x times cotangent x dx. You may have learned that back in the day, the derivative of regular cosecant x is negative cosecant x times cotangent x. You may have learned that. Well, look at the similarities. What this means is the integral of cosecant x cotangent x is going to be negative cosecant x. Now, I know that this is a negative, and if I wanted to apply the negative and do a little bit of reverse, that's fine, but I'm not going to. What I'm going to do is I'm going to rip out that -3 because I can. I have the integral of cosecant x times cotangent x dx. I now know that the integral of cosecant x cotangent x is negative cosecant x, and then we're going to attach that plus c. So negative becomes positive. 3 cosecant x plus 3. That's my derivative. Nope, just kidding. That's my integral. I need to take a break. Thanks for watching. Evaluate the indefinite integral 12x cubed times the quantity 3x to the fourth plus 4 all to the fourth power. Now what I could do is I could FOIL this out and then FOIL it again and then FOIL it again and then distribute to 12x cubed, but that would be an absolute nightmare. So what I'm going to do is use U substitution. It's very similar to chain rule for derivatives where it looks like you have a function living within a function, but U substitution is basically saying I need to find, there's two parts here, the 12x cubed and the stuff inside the parentheses. You're basically saying, is there anything that if I were to take the derivative of it, I see floating around in the problem? Yeah. It looks like that if I were to take the derivative of something x to the fourth, I would get something x to the third. So what I'm going to do is I'm going to let u equal 3x to the fourth plus 4. Okay, I take the derivative of that. Du dx means the derivative of u with respect to x. 4 times 3 is 12. 4 drops down to a 3, and this 4 goes away. Now what I need to do is I need to solve for dx. The way I solve for dx is I multiply both sides by dx, and as you do more of these, this process will go a whole lot faster. But if I multiply both sides by dx, I have du equals 12x to the third dx. dx isn't all by itself yet. I'm going to divide both sides by 12x to the third. Divide both sides by 12x to the third. And now I have dx equals du over 12x to the third. Now, why does that matter? Because what I'm going to do is I'm going to replace what I called u with u, and I'm going to turn dx into du over 12x to the third. And you'll see the magic happen. So I have 12x to the third. That whole thing is now u to the fourth, and dx is now du over, no way, 12x to the third. Now, what's magical about that? Well, 12x to the third over 12x to the third cancels each other out. So now I have the integral of u to the fourth du. The integral of u to the fourth du is 1/5 u to the fifth plus c. Now, before I circle this and call it a day, I'm not done. Remember, we were not given u in the original problem. We were given something with x's in it. What I'm going to do is I'm going to rewrite this guy. turn u into 3x to the fourth plus 4. So my final answer is going to be 1/5 parentheses 3x to the 4 plus 4 close parentheses to the 5th power plus c. That is my guy. That is my answer. That is U substitution, dealing with polynomials and power rule. Fun! Evaluate the indefinite integral. All right, so what I have here is I have a rational function. X is on top, x is on the bottom. And the way I'm going to approach this is with U substitution. What you do with U substitution is you look at what you have. So I have two things here, the numerator and the denominator, and see if I were to take the derivative of one, that I'd get the other, or see if that's floating around somewhere in the problem. If I were to take the derivative of the denominator, I would get that guy right there. So what I'm going to do is I'm going to let u equal the denominator, 4x to the 5th plus 3. Now what I want to do is I want to take the derivative of that, du dx equals, let's drop that, make that 20, x to the 4th plus 3 goes away. What I want to do is I want to turn this into dx. So the way I turn this into dx is I multiply both sides by dx. So du equals 20x to the 4th dx. Divide both sides by 20x to the 4th. Divide both sides by 20 x to the 4th, and now writing it out a little bit nicer, dx equals du over 20 x to the 4th. Let's go back to my original integral. I can replace a few things. I know that I didn't do anything with 20x to the 4th, so that happens. I called u 4x to the 5th plus 3, so let's call u, and I called dx du over 20x to the 4th. Now, why is this fantastic? Because these guys cancel out, and that's what you're hoping will happen. If you're going to use U substitution, you need all of your x's to go away, otherwise you chose the wrong u. So now what I have is perfect 1 over u du. The integral of 1 over u is ln of u. I'm going to add that arbitrary c. I'm not done. I said that u was 4x to the 5th plus 5, so my final answer is going to be ln of 4x to the 5th plus 3 in absolute values plus c. So a little bit of rationals, a little bit of ln's, a little bit of u, a lot of bit of me, and a lot of bit of fun. Evaluate the indefinite integral. We have 10 sine of, let's put this in parentheses so it looks a little bit bigger, of negative 2x times e to the cos negative 2x. What you want to do is whenever you have weird looking integrals, like we have something times something to the something, we want to try to use what's called U substitution. And when you use U substitution, you want to pick a U that if you were to take the derivative of it, you see that derivative floating around somewhere else in the problem. Now, what I'm going to do is I'm going to let U equal cos of negative 2x. I almost said cos minus 2x. It's cos of negative 2x. Because if I take the derivative of cos, I will get something like sine, which is what I have there. Things will cancel out. U substitution, that's what you do. So what I have to do is I have to find the du dx. So du, the derivative of cosine of negative 2x, involves chain rule. So you take the derivative of the outside stuff, which is negative, and I'm going to purposely leave a little space here, negative sine. Okay, the derivative of the outside stuff is negative sine stuff. Keep the inside stuff, but multiply everything by the derivative of the inside stuff. So the derivative of the inside stuff is going to be negative 2. So I have a double negative going on here. which I'm just going to say du dx is going to equal 2 sine negative 2x. Now what I'm going to do is I'm going to multiply both sides by dx. That gives me du equals 2 sine negative 2x dx. I'm going to divide everything by this. That way it gets dx all by itself. Divide everything by 2 sine stuff. And what I'll end up with is dx equals du over 2 sine negative 2x. So let's rewrite this guy out knowing what I know. I have the integral. We could bring that 10 out. Why not? The integral of sine of negative 2x times e to the u. And instead of dx, I'm going to write out du over 2 sine of negative 2x. The magical thing that happens here is the sine stuff disappears, which should happen. Anything that involves the x's should go away if you do this. Should have crossed all that out. All right, 2 is on the bottom, 10 is on the top. This becomes 5. So I have 5 times the integral of everything is gone except for e to the u du. Okay, the integral of e to the u is e to the u. So I have 5e to the u plus c. What was u? Well, my final answer is going to be e to the cos negative 2x. Don't forget about your constant floating around at the end. That is my answer for this indefinite integral. Fun, 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 fun. Evaluate the indefinite integral 16x squared times secant squared of 4x to the fourth minus 2. All right, so when we have a product of functions, which is what I have, and I'm being asked to integrate, I'm going to try to find a u. That if I were to take the derivative of it, its derivative is floating around somewhere else in the problem. If I were to take the derivative of something x to the fourth, I would get something x to the third. So I'm going to let u equal 4x to the fourth minus 2. This is called U substitution. I have like a billion videos of U substitution, like maybe 3 or 4 of them. All right, what you do next is you take du dx, which means the derivative. You get 4 times 4, which is 16. That 4 drops down to a 3, and that minus 2 goes away. Oh, look at that. The same exact thing over there. It's as if that's supposed to happen. Now I need to solve for dx. So you're going to multiply both sides by dx, giving you du equals 16x cubed dx. In order to get dx all by itself, divide everything by 16x squared. So you're going to have dx. I'm just flipping things around. I'm dividing and flipping. Du over 16x cubed. Now I'm going to rewrite this integral. Okay. 16x to the third times secant squared. That became u. And dx became du over 16x cubed. Good things happen because the 16x cubed and the 16x cubed goes away. If you're doing integration by substitution or U substitution, if you are trying to get u in here, all the x's have to disappear. If that doesn't happen, you did something wrong. You selected the wrong u. So now I have the integral of just regular old secant squared u du, no attachments. The integral of secant squared stuff is tangent stuff. So regular old tangent u plus c. Can't circle it because the original problem didn't have u in it. I called u 4x to the fourth minus 2, so I have to rewrite this out and say tan 4x to the 4 minus 2 plus that arbitrary constant. Another U substitution problem down. 10 U so much. Oh. Like and subscribe. Approximate the area under the curve. All right, so what I'm being asked to do is I'm given a function here on an interval of -5 to 3. I'm going to actually be as approximate as humanly possible, right? I have, let's see how many boxes that I have. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. 25, 26, 27, 28, 29, 30, 31, 32. These combine to make 33. These combine to make 34. These combine to make 35. And these combine to make 36. Now, the CUDA software answer is 36 because that's where I stole this problem from. In reality, what you could probably do is count the entire whole squares and then maybe do some half squares and get a more accurate answer. But, what they want us to do is they want us to turn this problem into these rectangular things where it looks like the rectangle is hanging all the way to the left side of whatever double interval, I almost said integral, it gives us. And that's that. Evaluate a definite integral between -1 and 3 of this polynomial right here. Now, what we do is called the fundamental theorem of calculus. All right. You take the integral, you find whatever that is, okay? And capital F stands for integral. And then what you do is you take, this is called the upper limit, and subtract the same exact integral and plug in the lower limit. This is the fundamental theorem of calculus, the FTOC. All right, so the first thing I have to do, as I erase that, is I have to take the integral. No plus c's in this. We are finding absolute answers. All right, you're taking the integral of -x to the third plus 3x squared plus 1. So a lot of power rule going on here. So we have -1 over, take that 3 plus 1, x to the 3 plus 1, plus 3 over x, which is 2 rather, plus 1, x to the 2 plus 1, plus, if it's just a constant, when you take the integral of a constant, attach an x. And then these little things over here are just reminding me that I have these limits of integration that I'm going to eventually plug in. So let's clean this up. -1/4 x to the 4th plus 3 over 3 disappears, x cubed plus just an x with my limits being 3 and -1. Now, the fundamental theorem of calculus says is I'm going to take this whole thing, plug in 3, minus take this whole thing, plug in -1. So a little bit of math. Hopefully I saved myself enough room. I feel like I didn't, but I guess we'll find out. -1/4. My upper limit is 3, so 3 to the 4th plus 3 to the 3rd plus 3, close it, minus -1/4. -1 is my lower limit, to the 4th plus -1 to the 3rd plus -1, close that. All right, let's see how much math we can do and not make any silly mistakes, which is bound to happen. Bounds, that's funny. Math humor. Math humor. All right, we've got -1/4 times 3 times 3 times 3 times 3 is 81. So -81/4, don't like that, plus 3 to the 3rd, which is 27, plus regular 3, which is regular 3, minus -1 to the 4th, which is regular 1 times -1/4, so -1/4, plus -1 to the 3rd, so -1, plus -1, so -1 again. All right, let's change colors. All right, so I'm just going to use decimals because that's probably the easiest way to go. That's negative 20.25, right? Negative 20.25. This guy becomes 30, so negative 20.25 taken away from 30 is 9.75 minus negative a quarter minus 2, so negative 2 and a quarter. All right, double negative becomes a positive. 9.275 plus 2.25 is going to give me a nice 12. And that's the fundamental theorem of calculus for you. You can't spell fundamental theorem of calculus without fun. Oh, the answer is 12. All right. We have a definite integral of 2 cos x. Upper limit is negative pi over 6. Lower limit is negative pi over 4. This uses the fundamental theorem of calculus, which says take the integral, plug in this guy, minus sign, plug in that guy. So hopefully we know our trig. I know I do, but do you? The integral of cosine is sine, so the integral of 2 cos x is 2 sine x. So let's write that out. 2 sine x, where the upper limit is negative pi over 6 and the lower limit is negative pi over 4. The fundamental theorem of calculus says, let's write all that out. Positive 2 rather, sine negative pi over 6 minus, rewrite it, 2 sine negative pi over 4. All right. All right, this becomes, I think that's negative a half. I'll double check these at the end to make sure I'm all right. Minus 2, that's negative root 2 over 2. I do know that. So let me do that. Negative root 2 over 2. Let's see. We got a little bit of cancellations. Let me quick pause and make sure I did that right. I did it right. All right. So negative 2 or 2 times negative a half is 1. Negative 1. Ugh. Negative 1 minus negative root 2. And so I'll just put my answer up here as negative 1 plus root 2. So not pleasant. Not a pleasant answer at all, but, I hope it's right. I think it's right. So there you have it. All right, we have to evaluate the integral between negative 1 and 1 of e to the stuff. Now, this is fundamental theorem of calculus, but what this also is U substitution. So what I'm going to do is I'm going to let U equal my 2 to the x minus 2. 2x minus 2. Because I can just take the integral of e to the u, it's just e to the u. Easy peasy lemon squeezy. Now what I have to do is I have to turn du and find du dx. So du dx is just going to be the derivative, which is 2. Multiply both sides by dx. So I get 2 dx, divide both sides by u, or 2, and du is equal to dx. Now I'm going to rewrite this guy knowing that you're going to become u and you're going to become du over 2. So I have the integral between, and let's just be specific, x equals negative 1, x equals 1, because the original problem has to do with x's with respect to x, of e to the u du over 2. I'll write this out as 1/2 and then do the same exact thing. Might seem a little, I don't know, a little much, but why not? Why the heck not? All right, so this is the same exact thing, just me taking that over 2 and ripping it out and making it a half. The integral is e to the u. So I have 1/2 e to the u, where my limits of integration are x equals 1 at top and x equals negative 1 on the bottom. U is 2x minus 2. So I'm going to rewrite this as 1/2 e to the 2x minus 2, or my limits of integration are 1 and -1. So I'm going to rewrite that and plug in 1. Let's get a different color here. 1/2 e to the 2 times 1 minus 2. It's going to make life easy. Minus 1/2. So same exact thing, but now plug in -1. 1/2 e to the 2 times -1 minus 2. Close it. 1/2 times e to the 0, because 2 times 1 is 2. 2 minus 2. E to the 0 is 1/2 times 1. So I have 1/2. That's it. Minus 2 times -1 is -4 when all this is said and done. So I have 1/2 e to the -4. So maybe what I'll do is I'll write this up here, way up here in a different color. We have 1/2 minus 1 over 2 e to the 4th. And that's my guy. Fun, 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 fun.